Okay, so last time we learned how to compute commutators of the modes of generators using some counter-integral techniques. So we found how to express such commutators in terms of local OP of the fields, and the formula was like this. So we had an expression for the action of some operators, like I acting on O. Maybe we can write it in terms of the OP. So we have some operator that has a OP. We have some current which has some OP with the field O, which looks like sum over I n O of W divided by Z minus W to power delta I plus n. And we found that commutator of two such modes acting on field O is some, if you have another current of this form, so this is 0. Actually, let me draw this picture again, because I forgot all the signs, so it's better to recover this once again. Yes, so we first act with a J, and so we put some J of W. And then we act with I. So we put here some I of W. Minus permutation of ij, and it equals to I of z. So it equals to the integral where we have here w, and z goes around w. So here is j of w, I of z. So outer integral is in w, and inner integral is and we also have the factor w to delta j plus n minus 1, and this, so this integral is around 0, and this integral in z is around w. Okay, it is m. So I of z, j of w. Of 0. So we have this identity, which we will use a little bit later. And last time we used it to compute the commutator of modes of this U1 current G of Z, which has a OP with itself of the form 1 over Z minus W squared plus regular. So this local OP gave a commutator like Jn J M equals to n delta n plus m 0. And today let us compute some other commutators. Namely, let us compute the commutator of this J with components of the energy momentum tensor. So we have let us say how to write the OP of the energy momentum tensor with arbitrary primary field, or well, in general with arbitrary field. So components of this expansion, the generators which appear there, are called Virasoro generators. Well, maybe you can write n from minus infinity to n, something like that. So these L's are called Virasoro generators. And we know, for example, that if this O is a primary field, then this series terminates. And we know its singular part. So who remembers what is the OP with Q of Z with the primary field? This is primary. Yes, there is such term. Mm-hmm. 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 Thanks. Yes, thank you. So then there is now we can compare these two expressions and say that L0 acting on O delta equals to delta O delta. L minus 1 acting on O delta is d O delta. And higher ends with L greater than 0 acting on O delta and give 0. And for over ones, we will have L minus 2 and so on. So in particular, this first regular term will be L minus 2 acting on O delta. Mm. And by the way, concerning this L minus 2, there is the observation that in principle we can take O delta to be identity field. Right, it is primary, and this OP will be regular, and this first non-trivial term, therefore, will be L minus 2 of 1. So, remark. T of Z times identity of W is L minus 2 times the identity operator of W plus Z minus W and so on. So if we now send Z to W, we can just say that T of Z is L minus 2 acting on identity of W. So. But at the moment, we don't know who these L's are and so on. So they, of course, from Virasoro algebra, but we need to derive it. But we know that there is such an identity. And in principle, we can say the same about this field J, that in the same way J of Z is J minus 1 acting on 1. Hmm? Yes, thank you. Okay, but what I want to show now is the relation in this commutation relation between the modes of T and J. So I want to apply this formula for the case when O is J. So so T of Z with J of W will equal to J of but actually we can do this with any field. Now let us do it with any field, supposing that this other field is also some integral of motion, in the sense it can act on the space of fields. So let us compute the commutator between modes of T and modes of O. So, so if you write it for J, then it will be something like J of W. No, actually, we need to know that J is primary. So it's some extra computation, which we'll do a little bit later. So commutator of ln with O delta m will be, so this integral like this, and here we substitute this OP. All this acts on some field O, which stays at 0. So we need to compute a residue at this point, which gives n plus 1 times the 2n. Right? So this and the second term is W to delta plus m plus. No, is it correct? Minus 1. So here we have derivative of this field, and so we need to integrate this by parts. So it will give the overall power and the coefficient will be so we have n, which is so one n comes from here, another n comes from here. So it will be n times delta minus 1. Plus minus m, just minus m, and this delta, which is not multiplied by anything, will cancel with this delta. So all delta of w. And all 0. So now it is an overall prefactor, and this integral is the action of m plus n's modes of O delta on this field O. So it is O delta m plus n acting on O computed at 0 times n delta minus 1 minus m. So we found this commutation relation that commutator of ln with O delta m is delta n delta minus 1 minus m delta n plus m. However, any questions about this formula? Hmm? Yes, of course. And and then we can study some particular cases. So, for example, we expect that this J of Z should be in the primary field, so it should transform like one form. And in principle, it should be true because it is a symmetry generator. So a symmetry generator should transform as one form, otherwise we will not be able to integrate them. It will mean that we lose the symmetry. And from our previous consideration, it looked like this symmetry is preserved in the quantum theory. But the real check that tells us that some field stays primary even at the quantum level is the computation of this OP in the corresponding quantum theory. So you should do this for this case of free boson. So and let us do this. So, any questions? So we computed energy momentum tensor in the classical theory, and in the classical theory it looked like 1/2 J of Z squared. But if we try to write something like this in the QFT, it is simply not defined because any correlator that contains J of Z will contain a pairing of J of Z with itself, which is infinite. So to define it properly, we need to take a normal ordering. And it can be understood either by saying that we exclude pairings of J of Z with itself, or we can say that it is the limit J of Z squared, it is the limit when epsilon goes to 0, J of Z plus epsilon over 2 J of Z minus epsilon over 2 minus 1 over epsilon squared. It is the same because pairing of these two fields is 1 over epsilon squared. So we first subtract the term that contains their pairing and then send the distance between these points to 0. Right? And actually, this representation is in some sense better than this one, because you can see what are the possible implications of this definition. Namely, if we perform some coordinate transformation, for example, conformal transformation, this shift written in coordinate z will become a little bit different from the first and for the second term, and corresponding asymptotics when epsilon goes to 0 will slightly differ from 1 over epsilon squared, and it will mean that this object will get some non-trivial extra term in the transformation. It will be proportional to the identity operator, but it shouldn't necessarily appear. So is it clear? So here it is. Here we have points uh, z plus epsilon over 2, z minus epsilon over 2, and after the transformation they will become w of z plus epsilon over 2, w of z minus epsilon over 2. So it will become w of z plus epsilon over 2 w prime plus epsilon squared over 2 w epsilon squared over 8 w2 primes. And this will be w of z plus epsilon over, minus epsilon over 2 w prime plus epsilon squared over 2 w 2 primes. So we see that, for example, 1/2 of this plus this is now not z, but z shifted by something. But we'll actually come to this consideration later. I just wanted to draw your attention to the fact that this definition is a possible source of anomalies. So when we do something like this, we should expect that something will break at some moment. And so first we will see what precisely breaks, and then we'll understand how to obtain this from the definition. Okay, so we take this energy momentum tensor, and let us check that J of z is actually primary. So we need to compute T of z with J of w. So it is 1/2 J of z squared J of w. So, and again, we can imagine that we are substituting this object under some correlator with other fields, for example, with other j's at different points. And we need to take pairings of all these fields with everything else. And there are again two types of pairings. Those which connect j of z with j of w, and that is singular in z minus w, and all other pairings. So we can write this as 1/2 times, so we write this two j's separately, j of w on this pairing plus 1/2 j of z, j of z, j of w with this pairing plus, so there are no other ways to put the pairing between these j's, so plus some regular term. So is it clear? Or are there any questions about this computation? So, hmm? Is it okay or not? Okay. So you can always imagine that if you write something like this, it means that this should pair with some other fields. This, and all three of this. Yes. So now let us compute these pairings. In a sense, let us write them explicitly. So this is this is j of z 1 over z minus w squared. Well, they actually coincide on this two terms because the pairing is the same. So you have such formula plus regular. And there is also one remark here that you see that if we consider the opposite OP, if we expand J of Z around T of W, well, if we no, how to say this? Oh, if we expand J of W around T of Z, we will get only the second order pole and no first order pole. So it will mean that a zero mode of no, wait, what? Yes, it will mean that a zero mode of J commutes with all modes um, of T of Z, which is of course true because we know that zero mode of J commutes with all components of Z, so it should commute with any other field. So, is it clear? Well, let me maybe finish this computation and then come back to that one. So, well, here we have such formula, but it's not enough to write the OP because at the moment we are interested in expansion around the second point. We always expand everything around the second point. So we need to expand this J of Z at W. So this will look like a J of W over Z minus W squared. It's a Taylor series. Plus d J of W over Z minus W, Z minus W plus regular. Like this. So this way we checked that T of Z, that J of W is primary for T. And now that remark. That we can write this formula as J of W T of Z is equal to 1 over Z minus W squared J of Z plus regular. Which means that commutator of so if we want to compute now the commutator of J0, well, actually it will be a double computation. So let us just write this identity for the primary field with dimension 1. So we check that J is primary with dimension 1. So let us write this identity in this case. So Ln with O delta M equals to minus M O delta M plus N. Like this, and then substitute O delta 0. So Ln with O delta 0 equals to 0. So this is what I wanted to say. it, O1M, O1M. Maybe let us write here JM, J0. So is it fine? So and this J0, so J0, and so it can be said also the other way. So using this OP, so J0, so thanks to the definition, action of J0 is just the integral of J of z dz. J of z is some field of dimension 1. And if we want to commute J0 with T of z, maybe J of W, dW. So if we want to commute J0 with T of z, it will be this difference. T of z, this contour, minus this contour. So it will be the integral around T of z. J of W, and here is T of z. But to compute this integral, we need to take the OP of J of W with T of z around this point z. And we see that this OP has only second order pole. It does not have first order pole. So there is no residue. So it is so it equals to 0. And actually, so in this case, it is some kind of trivial statement because J0 was some operator that commutes with everything. But it's not only the field of dimension 1. There are other examples, and since this argument does not depend on dimension, we will have other fields which commute with T of z. And one example of such fields will be screenings. Because remember, we have exponentials with parameter alpha and with dimension that depends on this alpha continuously. So we can take such fields and say that they also commute with T of z. So, is it clear? So in this integral, I'm using this OP, saying that it is a integral of dz over d w over w minus z squared, j of z plus regular. This equals to 0. So is it okay? So in general, if you have some field of dimension 1, some conserved current, then its zero modes commute with all symmetry generators. So in this sense, we can say that if you have some homomorphic symmetry, then there are zero modes of this symmetry which generate a non-homomorphic version of it. In a sense, some some symmetry without dependence on z. And all these generators commute with conformal generators. And this is an effect which depends only on this OPs between different fields. It relies on the fact that OP of dimension 1 field with T of z does not have a first order pole. Okay, so so we have this then this identity, and we also can also check the commutator of L0 with O delta. So commutator of L0 with O delta m equals to minus m O delta m. So it's another useful relation which tells that m's mode of some current shifts eigenvalue of L0 by minus m. And thanks to this identity, we can say that L0 is a kind of weight operator on all on all spaces which appear in conformal field theory. So in particular, if you take this identity, then we can compute the action of L0 on so let's write this. Well, let me write it here. So O0 acting on J minus M1, J minus MK on some vacuum. Let us call it vacuum alpha as before. So so there will be one term which contains J minus M1, J minus MK L0 acting on vacuum. And we need to know who is L0 on vacuum. We will study this later. And there will be one term that comes from these commutators. So who can tell what is this term? Oh, they were with minuses initially. Mm-hmm. Hmm? No. What do you mean? I'm saying that these coefficients were with minuses. So there was the mm-hmm. Yes. So m1 plus mk acting on j minus m1, j minus mk on alpha. So and if it is an eigenstate for L0, which is actually the case, if it is an eigenstate for L0, then this state will be also the eigenstate for L0 with eigenvalue shifted by M1 and so on mk. So. And if you remember the picture with a young diagram which parameterizes such states, then this eigenvalue of L0, or to be precise, the shift of this eigenvalue is precisely the number of boxes in the young diagram. And, of boxes. So, because they represent J minus M by a strip of length M. So, like there was this picture. Okay, M1 1 and 2. So if they're ordered from bigger to smaller, then it is in 3, and some of them is the number of boxes. Okay, we know this, and now the next question: how to compute the algebra formed by lns themselves? So. To do this, we need to first to compute the LP of T of Z with T of W. So naively, one would expect that it is that T of Z is a primary field, and we should have this relation with delta equals to 2. But it is not true. So we need to compute the OPE of these two energy momentum tensors. So now let us start from the most singular term. The most singular term appears when we pair both of these j's with these j's, and this can be done in two ways. So this is 1/2 j of z, j of z, j of w, j of w. So one way is to connect them like this. Another way is to cross these pairings like this. So there will be a factor of 2. Hmm? Yes, thank you. Yes, of course, yes. And here, yes, thanks. This is one term. Another term is when we have just one pairing, and there will be yes, so there will be 4 such terms, because so it will be 4 times 1/4 j of z, j of z, j of w, j of w. So one pairing is this, but we can also pair these two fields. We can pair this with this, and what else? This with this. So basically, we choose one of the field of the two fields here, and one of the two fields here, and pair them. So there are 4 such terms in total, and plus a regular term, j of z 1/4, j of z squared, j of w squared. So we of course neglect this. So now let us compute. This is 1 over z minus w to the 4th. So it is 1/2 over z minus w to the 4th. Plus j of z, j of w over z minus w squared. So it's almost the term we want. The only problem is that it is not expanded around w. plus. So we need to expand it now. This, and then the term with derivative. dj of w, j of w, or z minus w. And so it can be written as 1/2 to the fourth 2 times well, let me use the notation for the energy momentum tensor. So this is t of w, 2t of w, plus dt of w, or z minus w. So we can set the right hand side. And this was the computation for this free boson. And we have some, we have this term 1/2 here, and if we work with some arbitrary CFT, then this term should be replaced by arbitrary number c, c over 2, and this c is called central charge. And I told you before that if we want to define some CFT, we need to define its dimensions, delta i's, also the central charge, and structure constants. So the last ingredient, which defines CFT completely. So it's a very important object which in some sense measures the number of degrees of freedom in a CFT. For example, it decays on the renormalization group flow, reflecting the fact that renormalization group removes some degrees of freedom in theory. And some demonstration why it is related to the number of degrees of freedom is the fact that if we have some if we have two theories with T1 of Z, T2 of W, T2 of Z, so we have two different CFTs. The different CFTs mean that this T commutes with, between themselves. So T of T1 of Z, T2 of W is regular. So if you now construct the energy momentum tensor for for some of these two CFTs, T1 tensor maybe 2 of Z will equal to T1 of Z plus T2 of Z. So we can check easily using this formula that OP with this T tensor 1, T1 tensor 2 with itself will be the OP of the energy momentum tensor with a central charge C1 plus C2. So is it obvious from this formula? It's just the definition. So I want to call this way the theory that has an energy momentum tensor equal to the sum of the energy momentum tensors. Mm. Yes, you can construct it. And if you ask about primary fields in this theory, then it is also easy to construct them, because maybe let me write it here. So if you take O1 and O2, maybe so how to write O delta T1 of the O delta 1 of the it will be delta O, well actually for 1 and for 2 the same. So we define we define primary fields for both of these energy momentum tensors, and then we can consider products of such fields and compute the OP of this energy momentum tensor 1 tensor 2 of Z with just a product of such fields, delta 1 of W O delta 2 of W. So the question is, what will be on this OP? Everything with index 2 commutes with everything with index 1, and each of these fields is primary to correspond for corresponding energy momentum tensor. Yes, so it will be delta 1 O delta 1 1 over Z minus W squared O delta 2 2 plus d O delta 1 1 O delta 2 2 or z minus w plus but can we take this sum? Can we write it in some other way? So here it contains this derivative of the fold delta of the first field or the second field. Hmm? Yes. And here it will. Yes. Hmm? Yes, because they don't interact. Hmm? In a sense, why we cannot have other corrections. So in some sense it is limited by dimensions of the fields which we can have. Well, so no, the question is if we can construct some algebra with a higher order pole in this OPE. So usually some people say that we should get some fields of negative dimension, which is bad. And why we cannot have a third order pole in this OPE? This is because it is a symmetric expression. So it is not visible that it is symmetric in this representation, but we can write it as expansion around the intermediate point. So maybe let me erase something, probably this. Right. So this I will keep or not? No, probably. Recording. So T of Z, T of W, it can be written as C over 2 over Z minus W to the fourth plus so there are different ways to write it. Maybe it's easier to write it like T of Z plus T of W over Z minus W squared plus regular. So if you write it in the manifestly symmetric form, then we see that such expansion can contain only force and so maybe there is also another way to write this. Let us write it like this. 2t of z plus w over 2. All this is equivalent. And So if you write field in this intermediate point, that then we just don't have third order 4 because the left-hand side is symmetric. So, and the only place where we can have some field, in this case of dimension 0, is 1 over z minus w to the fourth. And these terms are, so this term is fixed because we know that this theory should be invariant under the global conformal transformations. So in T of Z, we will see how it is related, how this anomaly term is related to global and local conformal transformations. But the point is that if something is invariant under the global transformations, then these terms of the OP are fixed this way. Because they are related to L0 and L minus 1. Hmm? Hmm? No, invariant in the sense, well, covariant in the sense that it transforms as a differential form of appropriate weight. So actually, we don't even need the invariance under this inversion because it is fixed by a requirement that it should be symmetric. And these two terms, 2t of w and dt of w, are fixed by conditions that L0 and L minus 1 act by delta and derivative. So, and so this is, and this L0 is, this L0 corresponds to vector field z d in dz, and this corresponds to vector field d in dz. So these the terms are related to translation invariance and scale invariance of the theory. So, hmm?
Let's say we did the same reasoning for two primaries on the stress
Mm-hmm.
We try to put the OP.
Mm-hmm.
Why can't we repeat the same argument to say that, okay, we should get something like this that cannot have the poles bigger than a certain order and that should be symmetric. Okay, we let the constraint and OP.
What do you mean? So if you compute some correlator of primaries, then we can get something on the right hand side. But it will not be fixed because here to fix this first terms, we used some symmetry constraint. So to know that it is delta, that this becomes 2t of w, and this becomes derivative, we need to know first that t of z, which is in this position, is a generator of conformal symmetry, and that this field has dimension 2. In that case, it is t. So for primaries, you can get just any other primaries, depending on the theory. So.
What I meant is that, okay, if we, for example, take O delta of W with O delta of Z,
Mm-hmm.
so we get a combination of all primaries, but we don't get almost like these ones in general with some inverse function from that
Also, for all delta of w with all delta of z is 1 over z minus w to power 2 delta. So if delta is not a half integer, it will just be some branch point. So and plus some well, minus well, there will be this term, and there will be some over 1 of z minus w to power 2 delta minus and delta prime o delta prime of w plus some other terms. So there can be some trivial monodromies of this expression, and usually it will appear. So, cool. So are there any other questions about this? So here we were just lucky that all these singular terms are expressed back in terms of t of z. In other cases, we can have other fields in the right hand side. Okay, so let's go to the computation of the commutator, right? So let us take this formula written where? Here. And substitute 2t of this with delta equal to 2. So this is integral dw over 2 pi I w to n plus 1 on 0 on w so this is m plus 1 acting on O. T of z, T of w. So actually, we already computed this commutator for the primary field of dimension delta, and we can use this result. So we just need to compute the correction that comes from this singularity. So here's fine. So. So it will be the integral over 0 d w to pi I so well, plus kind of primary of 0.
So what is 0 t is just a primary operator.
Yes. Yes. So, so we need to take, we need to expand this z up to third derivative, and this third derivative contains a prefactor 1/6. So in total it will be c/12 integral w/2 pi w to n+1 n+1 n-1 w to n-2 all of 0. So in total it is n+1, and this integral equals to 1 when n+1 equals to 0. So it will be and plus primary. So it will be c/12 n cubed minus n delta n plus m 0. And now let us remember this commutator for primaries. So it equals to n minus m times O with index n plus m. So let's write it here. So this is the a relation that defines Virasoro algebra. And this contribution with central charge is called central extension because it commutes with everything. And from a field theory point of view, this extra contribution with central charge is called anomaly because it comes from quantum corrections. So here it appeared because of this pairing between J and J. So, and also we can study the structure of this algebra a little bit. So remember we had this algebra of vector fields minus n z n plus 1 dz. And it satisfied almost the same commutation relation, but without a central charge. Ln was Lm was n minus m, Ln plus m. We also found two subalgebra in this algebra of vector fields, and we can also see this algebra in the Virasoro algebra, because the central extension vanishes for n equals to 1, 0, and minus 1. So we can write that SO2 is in Virasoro, namely L1 was L. Let me write it like this. L0 was L1 equals to minus L1. L0 was L minus 1 is equal to L minus 1 and L1 with L minus 1 is equal to 2L0. And these three generators that correspond to these global transformations, translation, scaling, and this special conformal transformation, which is which involves inversion. So they form a non-extended SO2 subalgebra.
Is this the only way to extend the Virasoro
Yes. I don't know if it makes sense to do this in computation, but you can substitute here. Well, actually, you can try to do this at home and see how long the proof is, because I don't remember already. But in principle, you can try to write that there is some function of two. Yes, of 2 or just of 1. No, in principle, we should write some function of n and m, which is anti-symmetric. And then first, ask that this algebra satisfies Jacobi identity, and second, this function is defined up to n minus m times function of n plus n, because naively we can obtain some kind of central extension by shifting all n's by constant. So this should be removed, and there is a kind of problem of computation of some cohomologies of this algebra. So we need to find functions that satisfy the set of Jacobi identities, and at the same time they are defined up to functions of special form. So and the answer will be only this one.
Asking the information with every other generator.
Yes. But from dimensional reasons, this should be some identity operator sitting in that place. And in principle, if you think about such vertex algebras where we have where everything is packed into currents, and all relations are written in terms of OPs, it is clear that it is more or less a unique procedure, because we have only this fourth order pole, and we can put some operator there. All other extensions will not have in this form. But even if you neglect this structure and try to find some other extensions, there will be only one. So. Yeah, so I need to remember how complicated it is, and then if it is not very technical, I can try to show it the next time. Yeah. Okay, so we have this relation, and in some sense, this computation it changes a little bit this expected transformation properties of T of z. So originally we started with some field which was the 2 form. It had dimension 2, and now we have this non-trivial OP with itself. So we used already this formula for the commutator, so we will not need it anymore. And now we can try to compute here the transformation property of T of z under conformal transformations. So before we use this homomorphic conformal identity to find the OP of some primary field with T of z, and now we are using it in the opposite direction to find transformation properties from the known OPs. So like this formula that G, epsilon of T of W is the integral z over 2 pi I epsilon of z T of z T of W around W. So we need to expand epsilon up to third order for this term here up to the second, up to the first order, and the result is C over 12 epsilon 3 primes of z of W plus epsilon prime delta T of W plus epsilon W dt of W. Well, this is the Euro transformation law, and this is third derivative of epsilon. So we see that, again that it vanishes for a constant linear and quadratic epsilon. And now, so in principle, if we have this for infinitesimal transformation, we can integrate it back to find this cocycle for finite transformation. But I left this definition of G of z here precisely for this, because we can try to find transformation property of the energy momentum tensor, keeping in mind this definition. So let us try to do this. So it's for large transformations. We define T of z as how much? Okay. So we define T of z as J of z, T of z dz squared, maybe better to write. As 1/2, did I forget 1/2? Here, yes. Oh, sorry. This should be written as dz of z plus epsilon over 2 dz minus epsilon over 2 minus no, maybe it's fine. No, let's try it like this. So we have some T of z in one coordinate, and at the same time we can write the same in the other coordinate. So we can write T of z dz squared T tilde of z d tilde of w, maybe d w squared. This will be oh, sorry. Which is fine. So let us say that we are trying to compute something like this, but in a coordinate w, and we will subtract the same expression, but written in not in the coordinate z, but in the coordinate w, where we divide by not by difference of these points, but difference of w of them. So we kind of keep these points the same, but change the term which we subtract. So here we will have formula like j of w of z plus epsilon over 2, j of w of z minus epsilon over 2, dw, and this term to subtract will be d of w of z plus epsilon over 2, d of w of z minus epsilon over 2, divided by 2 w of z plus epsilon over 2 minus w of z minus epsilon over 2 squared. So now we want to compute the correction for this one-form transformation property. So namely, we need to compute the difference between t tilde of w dw squared over dz squared minus t of z. So these terms will cancel because they are just normal two forms. And the remaining term will be the difference of these terms which should be subtracted. So it will be dw of z plus epsilon over 2, dw of z minus epsilon over 2 over dz squared. This was sign minus dz squared this minus this simpler term, which is 1 over 2 epsilon squared. And they cancel because they are just well, I should write j tilde here, saying that it is the new field. But this field transforms just as the one form. So in a sense, it is primary field. And we already checked this. Wait, I wrote this normal order, but it should not be here. It should be like this. It's just product of the usual one forms. Plus, sorry. Yes.
Why the differentials the W
Hmm?
one and not evaluate it? I mean, they evaluate Z plus epsilon.
Yes, but this Yes, I just didn't indicate this values. But this doesn't matter, and because this differentials will have so here we can send epsilon uh, to 0 because how to say this, because the difference of these terms will be regular. So wait, what? How should we say it precisely? I think like this. Okay, so now we need to compute this difference. So so it will be 1 over 2 epsilon squared w prime of z plus epsilon over 2 w prime of z minus epsilon over 2 over minus over 2 w of z plus epsilon over 2 minus w of z minus epsilon over 2 squared. So we need to expand it as a series in epsilon, and you can cancel this 1 over epsilon squared term. So it looks like so here we have w prime so we need to keep terms up to epsilon squared, because we divide by denominator proportional to epsilon squared. This and so, and the next correction will be with third derivative, since it is odd. And the third derivative, so it's 1 over 6 times 1 over 8 times 2 epsilon cubed w 3 primes. right? And everything squared. So it is we maybe write it by, but we maybe divide everything by w prime. So this will be 1 plus epsilon squared over 4 w primes over w prime squared. So why did I put here minus? No, this is was plus, and this is this. Like this, and in the denominator it is 2 epsilon squared. 1 plus so this will be multiplied by another 2, 1 over 12 w 3 primes over w prime. Okay, so finally is so what is this? No, here I made a mistake. It is minus epsilon squared over 4, and because it is difference of squares. So in here will be 1 over 6. Okay, so we see that the first term cancels as it should be, and the second term gives a minus 1 over 12 w with 3 primes over w prime minus minus 3 over 2, right? W 2 primes over w prime squared. So, and this is called Schwarzian derivative. Actually, yeah. So this is minus 1 over 12 Schwarzian derivative of w with respect to z. So the answer is that this third derivative of epsilon, which appeared there, exponentiates to Schwarzian derivative. And so if you consider some global transformations, this is how the energy momentum tensor is corrected. So. Hmm? But here, yes, thank you. Epsilon squared over 6. And other terms are regular and epsilon, and I don't write them. In which? Yes, thank you. Yes, thank you. Mm-hmm. And in general, it will be not 1 over 12, it will be C over 12. So, if you perform some big conformal transformations, so, for example, if you map some domains of different shape, or if we map the theory from a plane to a cylinder, energy momentum tensor will be corrected by some function that depends on coordinate, but does not have any OPs with any fields, because it's just a function. So, and it means that if expectation value of t is 0 in some in one setting, it can become non-zero in some other setting. So. So, for example, it is 0 on a plane, but if we perform some double covering of this plane over, well, again, about the plane, it will mean that energy momentum tensor will have some non-trivial expectation value of the energy momentum tensor will have some non-trivial z behavior, which will mean that we have twist fields at the branch points. So probably we'll see it at some moment. But the point is that this correction is meaningful. It can give some information about theory. So it's not like some unpleasant term which should be ignored. So, and there are also other ways to see this Schwarzian derivative. For example, maybe. So, well, it will take just a few minutes. So there was this Liouville theory. There was this d bar phi equals to mu equals to 2 phi. There was this equation. So in this case, e to the 2 phi was 1-1 form, because it is a metric. Or we can see that from this equation it should be something like this. It is d bar of something, so the dimension is this. And but we also found, so there was an energy momentum tensor which is d phi squared, probably minus d 2 phi I forgot the sign, but something like this. And we knew that this energy momentum tensor comes from the equation d of e to the minus phi equals d2 e to the minus phi, well, d2 plus t of z e to the minus phi equals to 0. Maybe no, there should be minus sign here and plus sign here, probably. So we have this equation, and since e to the 2 phi is a 1 form, e to the minus phi is minus 1/2, minus 1/2, minus 1/2 form. And so we say the following statement, that if we transform it, if we perform some coordinate transformations and transform e to the minus 1/2 e to the minus phi as a minus 1/2 form, then this equation preserves this form, right? So we can say that e to the minus phi times dz to minus 1/2 is invariant. And you can write this transformation property of this energy momentum tensor, which follows from this prescription. Because namely, if you take this equation and perform some coordinate transformation, you need to write a derivative in some dw of z, and if you do this with the second derivative, it can produce in the first order term, right? So, namely, dw of z squared is 1 over w prime dz 1 over w prime dz. So it will produce something like 1 over w prime squared dz squared plus minus w2 primes over w prime dz. So there will be this term. But if you add transformation if you add an trivial transformation property for this field, this term will cancel. But you will get precisely this correction to t of z. A different way to see this is to say that phi transforms as minus logarithm of form of this weight and compute transformation property of t. So, and this is this Schwarzian derivative now in the classical setting.
So I didn't get this point. So the point is that if we try to do a transformation, the only way to keep the form of the equation is to transform t, also including the Schwarzian derivative.
No, the only way to transform this equation is to transform this kind of wave function as a minus 1/2 form.
Okay.
And we should find this. And it turns out that it transforms as to form of this correction by the Schwarzian derivative.
Okay, and if we transform e to the minus phi in that way, as a minus 1/2 form t, in this way, we keep the form of the equation.
Well, we just keep the equation in the sense that if it was satisfied in the original coordinate, it will be satisfied in the new coordinate with the transformed energy momentum tensor. So.
And so we can also do that classically by saying that the energy momentum tensor has a logarithmic. You said something about the
Since we should not necessarily look at this equation, we can also look at the definition of the energy momentum tensor and say that the transformation property of this phi is dictated by this condition. So we can do this directly. So, yes, I'm starting from this formula, not from this, but it is equivalent. And this is somehow quantum mechanical consideration that if you want to do something with Schrödinger equation by keeping Schrödinger, we should multiply the wave function by something. So if you change coordinates, we should multiply the wave function by something. If you want to preserve it of this form. Hmm? Yes. And this Schwarzian derivative also appears if you try to do WKB in a sense that if you have something like d2 plus u of z times acting on psi h squared d2 plus u of z on psi equals to 0. You can substitute this psi, this psi taking into account the first terms of WKB in the form. So I use this. So we can construct, we can substitute psi as 1 over square root of s prime e to 1 over h bar s. So s is a function. So if you substitute it here and try to expand it as a series, you will see only even powers of h bar, and you also see Schwarzian derivative between s and z. No, if you do naively by substituting this with some corrections in h bar, then you will have odd and even powers in this expansion. But all odd powers can be summed into just this term. So if you write this equation for s, then it will be manifestly h bar squared dependent, and the term which appears there will be a Schwarzian derivative. I don't remember precise formula, but you can just ask mathematically to compute this, substitute it, and see how it works. Okay, so are there any questions? Okay, so thanks for your attention. So, see you the next week.
I'll not be here next week.
Ah.
I'll be visiting my supervisor next week, so see you in 2 weeks.
Okay.
But I will try to see if I can log into the Zoom link, but I'm not sure.
But tell me in advance. So let me stop it. Tell me in